we are going to discuss the conservation of momentum over here. Consider an object of mass m1, I'll call this as object A, which is moving with the velocity u1. And consider I have a second object which has a mass m2, I'll call that object as B, and which moves with the velocity u2. Imagine they're going in the same straight line, and we'll consider that u1 is greater than u2. Then you know that m1 is going to collide with m2, and after this collision they're going to put forces on each other. m1 is going to put a force on m2, and I'll call it as force on B. And Newton's third law tells us that if A puts a force on B, then B puts an equal and opposite force on A. And so it's clear that now m2 is also going to put a force on A, and I'll call it as FA. Now, after the collision, what happens depends upon their masses, but what we know is that their velocity is going to change. So let's say that m1, I don't know whether it goes in towards the right or towards the left, doesn't matter, but let's just say it continues, but it'll have a different velocity, v1, and also m2 is going to have a different velocity, let's say v2. And what we are going to do is find the connection between the momentum before the collision and after the collision. To do that, I'm going to employ third law. The third law states that the force on A must be equal and opposite to the force on B. But I know from the second law that force on A is the rate of change of momentum of A. So I can just call this as change of momentum of A divided by the time it took, and there will be a minus sign. This is the change of momentum of B divided by the time, and this delta t is the time of contact, the time for which A was in contact with B, and which I can cancel over here. So I have delta PA is minus of delta PB, and now delta PA is the final momentum of A minus the initial momentum of A. Here's the final momentum of A, and here's the initial momentum of A. So it's going to be m1 v1 minus m1 u1, and this similarly is the final momentum of B. Here's the final momentum of B, and here's the initial momentum of B. So it's going to be m2 v2 minus m2 u2, and now all I have to do is simplify this expression and rearrange this. So I'm going to bring m2 v2 on this side and take m1 u1 on the other side, and we have a nice expression over here, and this expression is telling us that this is the total final momentum. This is the momentum after the collision, is over here, and this is the momentum which is before the collision, which is over here. So this tells us that momentum, total momentum after collision is equal to total momentum before collision. But there is a condition required for this, and the condition is that there must not be an external force acting on our system. These forces, Fa and Fb, are the forces which are internal to my system, and my system consists of particles A and B. So as long as there is no net external force acting on my system, the momentum of that system is conserved. That is the powerful principle of law of conservation of momentum.